Okay, recording. All right, so hopefully you guys got my email last night. The syllabus has been updated to reflect kind of the change in the schedule. One thing you'll note is that this week, we actually have 3 class days. The university has given us, or is however you want to put it, the university has given us Saturday as a 3rd class day for our Tuesday, Thursday classes. Obviously, but it's an asynchronous class. So what's going to happen here is this material, this is the hardest for most of my students. This week is the hardest material. And unfortunately, we only get 1 week to do it. So it actually works out really well. So what's going to happen here is I'm going to teach this to you today and Thursday. And what I'm going to require for Saturday is basically you can either watch my video of, like, if you can go to lectures and you can watch these lectures that are pre-recorded. It'll be the same, basically the same lecture that I'm about to give. Or what you can do is you can go to, or I'll send you a video of somebody else presenting it. So, and I guess what this does is it kind of gives you the option, like if you feel really solid on this material, you can be like, I feel solid on it. I don't need to watch more lectures, then fine. But I'm going to give you more resources on this, and I'm going to suggest that you go that way. I actually found this part of when I took this class, this part I really liked, but most students do not like it. So, all right, anyway. So what we're going to be talking about today. Wait, any questions about anything?
Your hair is looking very blue today. Did you like re-dye it, or is it?
I re-dyed it. Yes,
nice.
Re-dyed it. Thank you.
Private here.
I'm totally ready to go back to being a brown-haired guy, but it was just not the old color was just not going away. So I cut away as much of it as I could. And then I was like, well, if I'm going to be ugly, I might as well be ugly in my own way, you know, in a way that I appreciate. So anyway, so here we go. So we're going to do forces on planar surfaces. So this will be, sorry, this should be hydrostatic forces on planar surfaces. Okay, all this stuff we're going to do, it's hydrostatic, so it does not apply if the water is moving. Doesn't mean you can't use it in those cases. It's just not the entire force. Okay, so apply the hydrostatic law to evaluate. So this is the objective, the magnitude and direction. Direction of the resultant hydrostatic forces on planes. Okay, so what I'm going to do here, I need to open my PowerPoint so I can kind of just one second. Okay. So, so what we're talking about here is something along these lines. Okay, well, you know, I have a ruler, but I don't think this. All right, let's suppose we have a dam. Let's just imagine. Okay, and I want to think about what we're talking about here. So we've got a dam, and there's some water on one side of the dam. Okay, and let's say there's no water on the other side. Okay, maybe this is a levee, maybe it's a dam, who knows what it is. Okay, now we need to think about a few things here. So Okay, the hydrostatic law. Well, what's the hydrostatic law? Well, the hydrostatic law is dP dz equals negative gamma. Okay, and so what I want to do is I want to think about the pressures on this like dam that I've just drawn, and and I want to I don't want to think about the individual pressures, right? Because that's just a lot of work. There's pressure all over this dam, right? There's a pressure right here, and it's pushing against the dam. There's a pressure like right here, and it's pushing against the dam, et cetera, et cetera. There's like a whole bunch of them. There's also pressures on the other side. There's air pressure on this side, right? And so what's going on here is I don't really want to think about all of these pressures. So what I want to do is I want to take all those pressures that exist all up and down this side and all up and down this side, and all this whatever. And I want to just replace them with a single force. Okay, it's the resultant force of all of those pressures. Okay, and so what we typically would do is we typically say, well, okay, let's look at this side, the right-hand side first. And on the right-hand side, we've got, let's see here. So what's the pressure on the right-hand side? Can anybody tell me?
It's atmospheric.
Right, atmospheric. Okay, and technically there is some vertical variation in that, right? So technically the pressure, say like at the top of this thing, is technically a little bit less than the pressure at the bottom, right? Because the air has, because the air has, what's the word for it? It has density. But the density is so small that if you remember, we basically ignore the vertical difference in atmospheric pressure. So it's going to look like this. This is the pressure on the right-hand side, PATM. Okay, that's atmospheric pressure. And you know what? It's the same on the right-hand side too. I mean, on the left-hand side too, right? We've got PATM, and basically it just looks like that. Okay. So you should note right off the bat, something really nice is that on that top little bit, the bit that's out of the water, we don't have to worry about the resultant of the atmospheric pressure on the left and the right is that it all adds up to zero. So we don't really even need to worry about that. Okay, but we'll talk about that in a second. Okay, so once we get to this point right here, okay, this is what happens. The pressure as we move downwards, so if Z, so this is pressure as we move downwards, as this decreases because we move downwards in the fluid, the dP, the pressure increases. Okay, and that's where that negative sign comes from right there. It's because those have opposite sign, but by gamma. So basically, the pressure is going to increase, and it's going to increase at a constant rate as we move downwards through the fluid. So here we go. It's moving constant rate downwards through the fluid. Pressure's increasing. Okay, again, you're in a swimming pool, you swim down to the bottom, the pressure is going to increase. So I'm drawing, so this is the pressure prism. Okay, at least that's what we typically call this. Okay, so the slope of this line right here is gamma. For every meter you go down, your pressure increases by gamma. Okay, or I guess usually you draw it this way, rise over run this way. I guess gamma would be, yeah. Okay, so anyway, so that's what happens as we go downwards in the fluid. Now, what I want you to note is two things. First of all, this is why we're able to use gauge pressure. Okay, because if I just said, well, the pressure is zero everywhere, if I just said like PATM, well, let's make that zero. Why am I able to do that? Well, the reason that I'm able to do that is because if I draw a line right here, like this, can I draw? Okay, notice. Okay, all the pressure on the left and all the pressure on the right that is within this area cancel. Right? So if I could, instead of just saying, well, it's 101.325 kilopascals on the right and on the left, instead I could just say, well, it's zero everywhere and ignore pressure on the right and the pressure on the left. If I use absolute, then I have to worry about this pressure on the right. I don't want to worry about the pressure on the right. So I'm always going to use gauge pressure, and that way I don't have to worry about the pressure on the right. Okay. And by doing that, what that does, that means I'm only left with this pressure prism right here. And what I'm going to do is I'm going to say the pressure right here equals 0 gauge. Okay. So that's why I'm able to kind of like ignore the what do you call it? All right. So then the other thing that we want to do is I want to think like, well, what is the, like, I need a resultant, like total pressure. So like normally if the pressure were the same everywhere, I would just take the pressure and I would multiply times an area and I would get the total force on an object. However, the pressure is not the same everywhere. And I want to think about, you know, where does it, like, where do I apply this? So what we're going to do is for any planar surface, for any force, basically what I want to do is I want to take this pressure distribution, P is a function of Z, and I want to convert that into a single force. Sorry about the gross noises. I don't know if you can hear Rocky chewing on that thing. I want to convert that to a single force, which depending on the book, I forgot what your book uses. I think it's force of pressure. And I want to convert it to a single force, force of P, where I know the depth to, or where I know where it's acting. Okay. So, so how do we do that? Okay, first of all, can you all guess where this thing might be acting? Like, is it closer to the top or closer to the bottom?
To the bottom,
Yes. Now, what makes you say that?
because it's a triangle.
Yeah. And so the forces are generally stronger on the bottom.
Yeah.
That's correct. In this, well, I guess it depends on the shape of this gate, but well, it depends on the shape of this gate, but it will be closer to the bottom than it is to the top. Okay. So the other thing that we can do that I want to be, so okay, let's just approach this more organized. Okay. So the magnitude. Okay, how do we get the magnitude? Okay. And one of the things that I want to note is that if this pressure distribution, if it were even, then I could say, so if pressure were constant, then the force on this gate would equal the pressure times the area. Okay, right? Like, so if, let's suppose this gate were like on the bottom of something, like, let's say it's like the little thing holding like your bathtub water or whatever. So let's suppose we've got like water over, you know, just some plug, and there's like a drain down here or whatever. Well, the pressure distribution here is the same everywhere. Okay, so in that case, I would just take this pressure and I would multiply times the area of that plug, and boom, I would get the total force. Okay, but however, in this case, pressure is not constant. So instead, if pressure is not constant, we can do kind of a similar thing. And I could say then the force is the average pressure times the area. Okay, so what I could do basically is if I could mentally imagine that I went up to my pressure distribution, and what if I just said, okay, well, let's just do like this. You know, like, let's even out my pressure basically. Let's pretend the pressure is the same everywhere. Okay, I'm gonna make that the average pressure. So what I could think about doing is if I took this part of the distribution and I put it right there. Okay, and so basically I'm just gonna spread the pressure over the entire face, and then that should work. Okay, that should give me the force. Now the problem, of course, is, and that's just a magnitude, but the problem with that is, well, what's the average pressure? Like, what's the average? Okay, in the one that I've just drawn, you might guess that it's halfway down. And it may be, it all depends on what the cross section of this gate is. But the way that you do it really typically is that you say, okay, what is the average pressure? Well, the average pressure, if we remember, okay, pressure, I should have written this down already, but pressure equals gamma times Z. Okay, or gamma times, excuse me, the depth. Sorry, let's erase that. Gamma times H. If I measure H like this. Okay. So, so there you go. So that's, so what we can do is we can plug this down here and I can say, well, the force equals, instead of P bar, I'm going to use gamma H, that's the pressure, but I want it at the centroid. Okay, so we're going to put a little C here. I think that's the way your book does it. I prefer the bar, but you know, your book prefers a little HC. So that's the pressure at the centroid. The centroid is where the average pressure exists. Okay, and then the area. Okay, so this is the HC, that is the depth to centroid. Okay, which is the location where average, Rocky, chill out, buddy, pressure exists. Okay, so this, the centroid, okay, so the centroid, any centroid, so centroid, here's how you calculate it. Okay, let's see here. So I'm just going to do it in general terms. So X bar equals 1 on A integral of X dA. Okay, and you guys have seen that from statics. However, usually we just use a chart. And in this case, we're just going to use a chart in book or for the exam, or really what I recommend, or the FE equations. Okay, so in the FE equations, there'll be a chart to tell you where to find that centroid. Okay, so this is really the recommended way to do it. Okay, because obviously then you don't get your textbook for the FE, right? Or any time really in life. Okay, so any questions on that? So I want you to conceptually understand what it is we're doing. We're just looking for the average pressure. And the average pressure occurs at the centroid. So if I take that centroid and I multiply it times gamma, I'll get the pressure at the centroid, which is the average pressure. And I'm just going to multiply that times the area to get the total force.
This is a dumb question. So H is always going to be from the surface to the centroid, right?
Well, H sub C, H sub C. So this particular H is.
So we always take that as a reference. We cannot do like from the bottom to the top.
Ah, wonderful. This is not a stupid question. This is a wonderful question. Yeah, so H's, which are going to show up pretty commonly here, they're always going to be measured from the surface of the water down. Yes. And if you take them from the bottom up, it's going to create some problems. Okay, so, and the way to think about that is that the pressure starts to build from here down. Okay, it does not start from here and go up. Okay, so like if you were to ask me like, what's the pressure right here? Well, the first thing I need to know is how far from the surface I am, right? And it doesn't matter where you ask, like I'm gonna have to go, okay, you know, so this is my reference always, it's the surface, okay? And, you know, we're gonna talk about that in a second because it's about to get a little bit annoying.
Dr. Wagner,
Yes.
I wanted to ask you and make sure I have this clear. Total pressure is always going to consist of what we've calculated as an average pressure. Like you're going to have to find that first if you're looking for the total pressure.
Well, we're never looking for a total pressure. We're looking for a total force. But,
Total force. Okay. So that's going to consist of you finding an average pressure.
right. We're going to find an average pressure and then we're going to multiply times the area over which it's acting.
Okay, perfect. Thank you so much.
You're welcome. So I should also note, with that in mind, this area that we're talking about, that's the area of this gate right here. Okay, so it's got a, you know, a vertical component, but then it's got another component that's going into or out of the page. Okay, it does not include the thickness of the gate. The thickness of the gate has no bearing on this whatsoever. Okay, like we were not worried about this thing right here, not important. Okay, I don't know how to say not important, you know. but not important. Okay, and so I see students make that error all the time. Okay, so so if I guess one little caveat, if the surface of this is under pressure. So like if instead of having P equals 0 gauge at the surface, if instead for some reason P does not equal 0 gauge, okay, then add the surface pressure to the pressure at the centroid. Okay, so then we would say, well, F equals, I guess it would be P bar A equals, let's see, so P bar is going to be, let's see, so it's gamma HC plus pressure at the surface, okay, times the area. Okay, and I think you can see that from this drawing up here, like this bit right here. Okay, if it was pressurized somehow, you would just pretend like you've got a universal pressure acting over the entire thing. Okay, so that would be P surface times the area.
I have a question.
Yes.
Can we have two different liquids in a problem? That
You
would
could.
cause-
You could. I've never done that to my students, but you could.
Okay, thank God.
And what would usually happen in that case is, let's suppose we had two different liquids. What would happen is, okay, so the top liquid has to be more dense than the bottom liquid. So basically what would happen is we'd have, oh no, don't do that. Okay, so what we would do is we would have, okay, so let's see, so it would be like this. Let's say this is the top liquid. Okay, and then the bottom liquid has to be more dense than that. Right, so it's more dense, so therefore that line is steeper. So what you would do in this case, what I would recommend is you do this, okay, you say, okay, well, here we go. I'm gonna do this top one, this top force or pressure prism, and I'm gonna replace all of that with a force like this. And that would use this equation, right, where is it? That would use this equation right here. Okay. And we'd have to figure out where it acted, using the centroid of that shape. Okay, this bottom bit, what I would do is I would need to figure out the pressure right here, like right at that interface between the two. And I would treat that like a surface pressure because it's going all through the whole thing like that. And then I would do gamma times the HC for this bit right here. So basically you would have three forces. One force would be this one. One force would be based on this triangle, and it would be acting like right here. Okay, and I'm going to show you how to figure out where it acts in a second. And then the third one would be this bit right here, which would be evenly distributed over that whole shape. Okay, so you'd have three forces. So yes, that could happen in real life. I don't really know of times that people have dams that are like, the top bit is an oil and the bottom bit is water or something along those lines. But I've never actually asked a class to solve that problem. Maybe I will one day. All right, let me throw this away and let's. Okay, any questions on this? By the way, the focus of today is really to get into the questions. So let's, I'm going to delete all this. Okay, because this stuff is like, it's a little bit esoteric when you're looking at it like this. But unfortunately, what happens is most of my students, they learn how to do these problems and then they don't really know what it is they're doing. So if I ask a problem in a slightly different way or whatever, like it throws them for a loop. I think some people think they're like trick questions. Nothing is ever intended to be a trick, not by me. I'm sure there are professors that intend things to be tricks. But yeah, not me. So certainly never. But intent and what happens, not always the same. So okay, let's see what we got here. All right, so let's see here. All right, so then that's the magnitude. Okay, direction. Okay. Direction / location. Okay, direction is easy. Okay, we'll start with the direction. Okay, the force of pressure. Is that what I called it on the last slide, F sub P? Okay, sometimes you'll see it called like, I don't know, F sub R for resultant, force of pressure.
Yeah, that's how you did it.
Okay, I'm gonna keep my notes consistent. Okay. Always normal to the plane. Okay, so the direction is easy. Whichever way you draw the plane, the force of pressure is going to be normal. Okay, it cannot act on an angle. Okay, okay, where is its location? Okay, well, it acts at the center of pressure. Okay, so the center of pressure is kind of like, so it acts at the center of pressure. Okay, which I believe your textbook calls that location YCP. I believe. Okay, so the center of pressure kind of looks like this. Okay, this is not the same thing as the centroid. Okay, let's put not at centroid. Okay, so now I'm going to try to define that for you, and then we'll talk about it. So, and I'm going to define it with I'm going to draw two gates, and one's going to be on an angle and one is not. Okay, so so here's a gate like this, and here's another one. Okay, and this one is maybe the side of a levee, right? And they did the levee on an angle, and there's some kind of maybe this is, I don't know, a little sluice gate, or for some reason they want to be able to open the levee, let water into the the farm fields behind it or whatever like that or whatever. Let's see here. So we got some water here, we got some water here, or whatever the fluid might be. And let's put a little gate right here. All right, and here's the pressure distribution of this one. Okay, so here we go. Okay, now the pressure distribution that we're worried about in this case is from here to here. Okay, the pressure distribution on this one. Okay, note that pressure is always acting perpendicular. So we care about this bit right here. Okay. So now we have a few things that we have to identify when we begin these problems. And the first thing we need to identify is, what are we talking about? So we need to find this YCP. Okay, and we need to find something called, we need to define a few things. So the first thing I need the height to the depth to the centroid. Okay, so let's see. So like on this one, maybe the centroid is, let's say the centroid is right here. Okay, so this is going to be H sub C, the height to the centroid. Okay, and it's going from the surface of the water down to the centroid. Over here, like I could do the same thing. Let's suppose the centroid is right here. And so I can go like that. I should go vertical, and I should use my ruler. Okay, so here we go. This is the H sub C. Okay. So, and that's an important quantity because it helps us with our calculation of the pressure, right? Because we find the depth of the centroid, we can figure out from there what the magnitude of the force is, right? Because we do gamma times HC times the area. Now, on the other hand, there's this thing called a YCP. And so over here, this is the same thing as Y sub C. So Y sub C is the distance from the centroid. So here, let me go ahead and define some things here. Okay, so YC is the distance from the centroid to the surface of the water. And this is the key bit, along the face. Okay, so, and this one on the left, HC and YC are the same because if I travel along the face, I'm traveling from the centroid, which I can maybe mark it in blue or something. Here's the centroid, here's the centroid. Okay, if I travel along the face, travel along the face up to the surface of the water, right? That's the exact same thing as the HC. Okay, on the other hand, if I go over to this one on the right, and I started the centroid, and I travel along the face until I get to the surface of the water, it's not the same as the HC. Okay, now, and this is the last little bit, right? Is that let me see if I get the name right. Yelitsa, is that how I say it? Okay, Yelitsa. As Yelitsa said, as she noted, okay, well, where does the force act? Well, it's going to act a little bit below, the centroid, right? Now, maybe it'll be a lot bit, but it's going to be below the centroid. Okay, so it's not going to be at the center point. It's going to be below that center point. So there's going to be a point, YCP, which is going to be like down here a little bit, right? So maybe if I draw it like that. So I'm going to call that line YCP, okay? So it's a little bit longer than the YC, okay? And let's see, do I have another color? Let's do red, I guess. So here's red, okay? And the YCP is always below, and that's where the force is going to act. So if I were to draw, an FP, it's going to act right there. Force of pressure is going to act at YCP. Okay. The center of pressure over here on the right, okay, same sort of thing. It's going to be a little bit below, and I'll tell you in a second how to calculate it, but it's going to be a little bit below the YC. Okay, and I'll tell you why I know that, or how I think about that. But it's going to be, it's again, the YCP is going to be measured on this angle. Okay, so it's measured along that face. Okay, and that's the real key thing. Okay, Y's are measured along the face. Okay, H's are measured vertical. And so this is the FP is going to be right here. Okay, now the way that I know this and the way that I think about where the FP act or where the center of pressure is what I imagine is, I wish I could like grab a force or whatever. But what I imagine is, I'm going to kind of just draw this gate kind of isolated over here. Okay, and I've got these forces on the left-hand side. Okay, if I wanted to balance those forces with a single force, a single FP, over here on the left-hand side, we have to think about like, where would you put it, right? I have a single force and I'm going to put it on the left-hand side. Where am I going to put it to balance those forces, right? If I have it the right magnitude and I put it right here, I think you could see that if I put it right there and the magnitude was correct, the sum of forces in the X are going to be 0. The sum of the forces in the Y are 0. But what's going to happen? statically, why would it not be okay?
It'll be a moment.
Right, there'd be a moment, right? This gate, if I did that, this gate's gonna open like this. Right? Same thing if I have the right force, but I put it down here. Okay, note that the gate is gonna do, the gate would open this way. Okay, if I put the force in the wrong place there. If I put it right in the middle, okay, at that centroid, okay, hopefully you can see I could balance the forces that way. But what's going to happen is this gate would open this way because there's more forces on the bottom than there is on the top, right? And so it would just kind of like the moment wouldn't work. So what I am trying to imagine is mentally I say, well, where would I put this, like my finger or whatever, or this force, so that it would balance out? And it's going to be somewhere below the centroid. Okay, so that's just kind of like emotionally, or not emotionally, intellectually, how I think about this. Okay, so, and that applies to either thought on the right or the left. So basically what we're going to do is I'm going to start, and this is the parallel axis theorem. It's maybe not written the way that you've seen it written, but the YCP, okay, you can see here, there's a distance between the YCP and the YC, right? So that is, what is that distance? Well, YCP is going to equal the YC, and we're going to add a little bit. Okay, what's that little bit we're going to add? Well, typically it's written down as, well, I guess I think about the way your book writes this, but the moment of inertia of that shape, I think your book is an XX like this, over YC times the area. Okay. The last thing to remember for, I mean, just the one thing that's like really, okay, so this thing right here, you get off of a chart and it is based on the shape. Okay, it is based on the shape, right? So, you know, like you guys will probably have memorized that for a rectangle, it's 1/12 base times height cubed, or for a triangle, it's 1/36 base times height cubed. If you haven't memorized that, it's okay. We'll get there. And then, I mean, obviously you're not required to memorize it, but usually just using these, they kind of, certain numbers kind of pop into your head.
Can you say what that's called again? You cut out for me.
Wait, what's the question?
Can you say what that's called again? You cut out for me.
Moment of inertia. Technically, it's called the area moment of inertia. There are other moments of inertia. Okay, and yeah, so let's go ahead and I'm going to go ahead and solve. I'm going to solve one of these, and I'm going to show you the way that I organize this all. But the problem is the way that I organize it ultimately kind of pulls away from intuition. So I'm going to constantly try to remind you to think about, you know, the intuition of what's going on here, and that sort of thing. So let me bring up the problem. Oh, interesting. Oh no, here it is. Okay. Okay. So, oh, looks like interesting. Okay. Anyway, so I got an example, and what I'm going to do is I'm going to erase. Oh wait, sorry. Oh yeah, I got the equation. Okay. Let's see. Can we clear all? Okay. So here's the example. In my notes, I call this example 1. So if you, okay, so it's just going to be example 1, and it looks like this. Okay. Given. Let's see. So we've got this thing. Okay, this is a very typical problem. They always ask these kind of the same way. Let's see, we've got seawater. Why did they do seawater? They did seawater to be annoying. There's the water. The water is, this is seawater. Okay, this is bottom. This is 15 feet. Okay, this little area right here. This is 8 feet. This is 6 feet. And this is some angle theta, which we don't know. Okay, so what's going on here is we've got some gate. And this gate has a hinge. So this right here, this is a hinge. This gate is 5 feet wide. So when you see something like 5 feet wide, what that tells you is we have a shape that is not we have a shape that's a rectangle. So like if you were swimming along and you were to look at this gate right here, so like you're like swimming, you're a little scuba diver or whatever, and you were to look at this gate, you would see a rectangle. Okay. So I mean, I guess I could try to draw that, but I think I would probably do a poor job. Anyway, so what we want to know is required. What we want to know is we want to know the force on the end of at the end of the gate. What does that mean? Oh, okay, right. So force on the end of the gate. Okay, so what that means is what is the force needed to keep this gate from opening? Okay, so we're assuming somebody's going to be pushing against it right here, against the end of that gate. Okay, what's the force to keep it from opening? And the last question is the force on the hinge itself. Yeah, so we call that just force on the hinge. Okay, I don't really like the force on the hinge question. That's very rare for them to ask you. They always ask you about, you know, what's the force on the end of the gate? Okay, so the solution here, it kind of boils down to, and I'm going to work this a little bit backwards because the logic is a little bit backwards. Or not really a little bit backwards, but it kind of tells you what it is that we need and why we need it. Okay, when you work these on a test, normally you're just going to like you're just going to like pile right in, because you know based on working a few of these that we're going to want the force of pressure and we're going to want to know where does it act. Okay, but I'm going to show you why we want to know those first of all. So this is a statics problem. It's a fluids problem also because there's, you know, pressures and stuff like that. So what we're going to do is I'm going to start with a free body diagram of the gate. Okay, and it looks like this. Okay, and I don't need you to spend a whole heck of a lot of time on this, but basically, here it is. You know, this is a gate. Okay, now we need to draw the forces on it. Well, we've got a hinge there, so the hinge, you know, the rest of the world can push upwards on it, so that's going to be H in the Y and H in the X. Right? What else do we have? Well, we've got this force right here, F, which is one of the things we're looking for. And then we've got the force of the pressure, and it's going to be acting perpendicular. Force of the pressure. Okay, and all of that combined, that's our free body diagram. So we could solve this right now if we knew what the force of the pressure was and if we knew where it acted. Okay, we don't know either. We know neither of those things, so we need to solve them. So what we're going to do is, so what I always do when I solve these, to make my calculations simple, is I'm going to use two equations. I'm going to put my equations over here. These are my tools right here. These equations are going to show up in every one of these. And one of them is that the force of pressure equals gamma HCA. Okay, and then the where it acts is YC plus IXX over YCA. Okay, and so those are my tools. And so I need to be able to get at what these things are. Okay, so what I do when I start these is you'll see in a lot, like it took me a little while as a teacher to kind of come up with this idea. But what I'm going to do is I'm going to think about this shape right off the bat. Okay, so what is my shape? Well, it's a rectangle. Okay, and the rectangle is 5 feet wide. So it's 5 feet along the bottom. So this is what I would see if I were this swimmer. 5 feet long. And now how tall is it? Well, what I'm going to see if I'm swimming in it is that it's 10 feet tall. Okay, how do I get 10 feet? Anybody?
So hypotenuse.
Hypotenuse, so Pythagorean theorem. Or if you want, this is a 3, 4, 5 triangle. Okay, so I just did Pythagorean theorem, but it's a 3, 4, 5 triangle, so it's like an easy one. Okay, so there's my shape. So then what I'm going to do is I'm going to start immediately by thinking, okay, what do I need out of these equations? Well, I need this HC. I need this YC. I need the area. And I need the moment of inertia. Okay, and I'm only going to think about the shape right now. I'm not going to think too much about the rest of the problem. Okay, so the HC, I'm going to go up to this thing. Well, this is a rectangle. The centroid of a rectangle is right in the middle there. Okay, so if I go over here, I'm going to draw it here. Okay, so one thing I know is in this direction, it's 5 feet. Not terribly helpful if I want the HC, which is going vertical. So this is what I want. That's the HC right here. So here's H sub C. Okay, let's see. So I'm going to kind of break it up into some smaller triangle in a little bit. So I note that this is the centroid. So this is also 3 feet this way because it's half of that 6, right? And then this distance right here, from here to the surface, that's 9 feet, right? Because I've got 15 here minus those 6 feet, so that's 9 feet. Okay, so the H sub C in this case is 12 feet. See if y'all see that. Okay, now I'm going to try to get the YC. Now the YC is a little bit more difficult because the YC has to go, remember, it's going to go along the face to the surface of the water. Well, the surface of the water doesn't really exist over here, so I'm going to need to kind of like extend it using a, whatever. And then, so the YC is going to go from here, this point right here, and it's going to go along the surface until it gets to there. Okay, so what I typically like to do is I like to find one of HC or YC, whichever one is easier, and then I just use trig to get the other. Okay, so we'll note that this angle right here is theta. Now I would do this using similar triangles. Like I would just notice that these are all 3, 4, 5 triangles. So because these are all 3, 4, 5 triangles, the vertical is a 3 to the diagonal, which is a 5, equals YC. Okay, that's that big red line I just drew to the vertical, which is 12. So that's how I would do this, is just using similar triangles. So this is going to be 20. Most of you all, however, I think are probably going to go another way, which is you're going to figure out what that angle is, which, hold on, let me get that angle real quick. So you'll use the inverse tangent maybe. The inverse tangent of the opposite, 6 divided by 8. And you'll get 36.8. Come on. And there's nothing wrong with doing this. It's just a little bit slower, equals 36.870. Okay, and then you'll do this, and then you'll just take this angle over here, 36.870. And you'll say, okay, well, I'm looking for, and you'll just do the trig. And you'll say, okay, well, so you'll say, well, the sine of 36.870 equals the opposite, which is 12, over the hypotenuse, which is what we're looking for, YC, just YC, excuse me. So this is probably what most of you guys would do. There's nothing wrong with that. It's just not the way that I would do it. So let's see here. Let's do the sine of that angle. And put that on the bottom. Times 12, and we get 20. Okay, so YCP is 20. Either way, or YC is 20. Okay, so either way. So this is 20 feet. Okay, so the key here being that that is along the angle. Okay, so now I need the area. Again, the key here is this is area that we're looking for is the area of the face. It's what you would see if you were swimming there. So the area of this face is 5 times 10, so that's 50 feet squared. Okay, and then this IXX or the I bar XX, you know, you see this written lots of different ways, but the moment of inertia is going to be 1/12 the base, which is 5 feet. Okay, again, you would look this formula up in a chart, times 10 feet cubed. Okay, so what's that? 5,000 divided by 12. I wish it wasn't 12. It always makes for ugly numbers. It's 416.67 feet to the fourth. Okay, so in my classes, we always keep at least 5 sig figs until the end. Okay, so now we're ready to go. Now we can just solve these equations. Okay, and that will make things easier for us. Okay, so what we need to do is we need to, well, we're just going to solve them. So F sub P equals the average pressure. So that's going to be, let's see, gamma HCA. So this is the average pressure. So FP equals gamma. Well, gamma, you guys probably haven't memorized yet, but you will have soon, 62.4 pounds per cubic foot. Okay, times the HC, which is right here, 12 feet, times the area, which is 50 feet squared. Okay, notice that this is going to get us units of pounds. Okay, actually, I had this all written down. I don't think pull this calculator out. 38,400 pounds. Okay, or 38.4 kips if you prefer. Okay, now we need to get the YCP. So the YCP equals, okay, we're just going to follow the formula. Okay, so let's just write the formula here, plus IXX or YCA. YCP equals the YC is 20 feet plus 416.67 feet to the fourth divided by YC, which is 20 times 50 feet squared. Okay, notice the units work out. We get feet plus feet to the fourth over feet cubed. So we get feet plus feet, so we end up with feet. So YCP equals 20.417 feet. Okay, notice that I'll stop for a second. I know you guys are copying. Okay, so notice that the YCP is just a little bit bigger than the Y. Okay, and part of that is because it's so deep. The deeper you get, you know, the closer these two things get to each other. Okay, and you can see this right here because of this thing right here. And really what it's saying is the less this variation across, this is from the variation across the face. This is from just being deep. Okay, so the deeper you get, the less the variation across the face matters. Anyway, so now we just have a statics problem. Okay, and so we're going to go back to that free body diagram, and I know everything that I need to know. Okay, and so, but by the way, there's another way to think about this that can be helpful. Is right, YCP minus YC equals 0.417. Okay, so it's helpful to think about this in either one of those ways. Okay, depending on what it is, depending on how the problem works out. Okay, but and I'll show you why I did it that way in just 1 second. So what I'm going to do is I'm going to erase all this stuff about the shape. Okay, I'm going to go right here and I'm going to say, okay, so now what I got is free body diagram of the gate, and now I can work this problem. So the force at the end of the gate, so that's this F. Okay, so let's just make this F equals what? Okay, so sum of the forces in the X direction equals 0. No, I don't want to do that, right? Because I can't solve that because I got two unknowns in that direction. I don't want to do it in the Y direction either because I got two unknowns in that direction too. No, I've only got one unknown, H of Y. I guess I could work that, but let's not work that. The way that you almost always solve these is you're going to do the sum of the moments, okay, equals 0. Okay, we're going to do the Z, whatever the into or out of the board direction is. But what we want to do here is we want to do this around the hinge. Because that way I don't have to solve for hx or hy. Okay, so basically I have two forces. Rocky, shush. Okay, so so I've got two forces. And what's nice about this is the forces, like the moments are relatively easy for these things. So the one is I've got FP, okay, and it's acting, it's going to cause this thing to spin. It looks like it's going to go clockwise. So it's going to get a negative times its moment arm. Okay, and then I'm going to go plus F times its moment arm equals 0. So the complicated bit here is thinking about what the moment arms are. Okay, for the F, it's pretty easy, okay, because we can just go right up here like this. And then the F is essentially acting right here. So its moment arm, it looks like if I go back to this drawing, is 6 feet. Okay. Now the FP, its moment arm is a little bit more difficult. It is acting on a right angle, so that's kind of nice. So what I need is I need this distance right here. Okay, and that distance can be a little bit annoying, right? And so what I want to make note of is that I know, if I go back to my original drawing over here, I know this distance, oh no. Okay, I know that this distance right here is 5 feet. Okay, the distance of this whole thing is 10. So this distance right here is 5 feet. Okay, that's to the centroid. Okay, well, this is how much further down that thing I am from the centroid. Right, so this distance right here could be written as 5 feet minus this 0.417 feet. Does that make sense?
Yes.
Okay.
When you were saying that, you were saying like this distance. I couldn't see where you were pointing at. I was looking for your cursor. Can you point again?
Okay, sorry. Okay, so let's see. So from here to the centroid is 5 feet. Okay. This force is acting 0.417 further down this face than the centroid. So this little tiny distance right here, that's YCP minus YC.
That makes sense.
Okay. So then at this point, all we need to do is solve this thing. Okay, so the last little bit I'm going to do here is I'm actually going to plug in the number for the FP. So I'm going to make this negative, what was FP? Oh, 38.4 kips. Okay, so if I solve this equation, I get F equals 29,300 and, well, I'm just going to leave it as 330 pounds. Okay, like that. And then from there, if I wanted the forces on the hinge, what I would do is I would say, okay, let's do sum of the forces in the X equals 0. And I would say, so I would look at my free body diagram and it looks like I've got HX, which is what I'm looking for, plus FP. And again, you guys would probably do a sine or a cosine here. FP is 38.4 kips. I'm actually going to use just similar triangles. I'm going to note that, well, this triangle is, well, let's say 3/5 times that force. So basically that force, if you look at it, it's going like this, but it's like triangle looks like this. So this is a 3 side, this is a 5 side, and this is a 4 side of that triangle. But you could go ahead and do that with a sine or a cosine if you wanted. And then I'm going to subtract this F right here, and I'll get minus 29,330 pounds equals 0. And I'm going to solve that and get HX equals 6260 pounds. Okay, now I'll do the same thing in the Y direction. Just going to delete this. Please don't hit my desk, Rocky. So I would say sum of the forces in the Y direction equals 0. And I would say, well, let's see here, H, Y. The only other force in the Y direction is the vertical force of our pressure. So 38.4 kips times 4/5. Again, you guys would probably use sines or cosines. If you can use a similar triangle, it's almost always simpler. And so the HY equals 30,720 pounds. Okay. And that's how you work it. Okay. I mean, there's just a lot of kind of like statics at the end. The only reason they make you do the statics is because what they're trying to do when they write these problems is to make sure you really understand where that force is acting. So usually you don't have to get the force in the hinge. Usually there's a force on the end that you're looking for. And that's usually the way these problems work. Okay. Questions on that? Oh, the last thing is we would round to 3 sig figs. So this you would report as, well, that would actually be fine, 6260 pounds. This one you would report as 30.7 kips. And the other one you would report as, 29.3 kips. So F equals 29.3 kips. Okay, 3 sig figs. All right, questions?
And why 3 sig figs instead of 5 this time?
So what I'm always asking you to do is report 3 at the end. So you keep at least 5 the whole way through. Really, ideally, you would just keep the whole thing in your calculator or not plug numbers in until the very end. And that way there'll be no rounding errors. But at the end of the answer, I don't want to look at all those sig figs.
Oh, okay.
Nobody's going to want that. Like, you know, if you're on a job or you're doing a calculation or whatever, what's going to happen as engineers is they're going to put in a factor of safety anyway. So if you calculate that you need to withhold, you know, the hinge needs to be able to withhold 30.7 kips and 6.26 kips in the 2 directions. They're going to go, okay, well, let's multiply those by 1.5, and that's, or 1.8 or whatever the factor of safety is. And that's like, we're going to get a hinge rated for that. So, you know, the precision to go out 5 sig figs is wasteful, right? But you don't want to have a rounding error on the way, because those can actually multiply and get pretty big. So, all right. Yeah. So that's just my preference. But, you know, different professors will have different preferences. The statics book I taught out of, or maybe it's this book. No, it's the statics book, has some ridiculous statement about, you know, you're never more than 2% sure or something, or 20%. I can't remember. It's complete ludicrosity. You just don't want to, you know, create any errors. You know, the last thing you can do is you can round right at the end. And, you know, if your client says, well, I want more significant figures, well, then you can go and look at you can just go, oh, well, I've got them. Totally fine.
And actually, sorry, one more question. We determined that the direction for the hinge horizontal force was to the right because it was positive.
No, so you mean for the answer for F?
Well, we had H sub X, right? That's the
yeah, I assumed it was positive and it came out to be positive. So yeah, it would be to the right.
Okay.
Yeah. Sorry, I didn't even think about that. But yeah, if I'm dealing with hinges or anything like that, I'm always going to assume that it's going in the positive direction. That way I don't confuse myself.
Gotcha.
I will do that all the time. All right, example 2. Unfortunately, we're only going to have time for 2 of these, I think. Maybe I'll get you all to watch the other example. All right, so we've got we've got a trough. Where did I get this example? I don't even remember. But this is a semicircle. Okay, I obviously haven't drawn it terribly well. but I wanted to do a non-rectangular shape. Okay, so there's some kind of trough, and maybe it's feeding horses, or I don't really know what these things do, right? I wish I could claim that I was some sort of like, you know, I did this stuff, but I don't know. It doesn't matter. Okay, so this is what's given. Okay, and it's full of water. Full of water. Oh, you know what? I made a mistake on the last one, didn't I? What's the mistake I made the last one? What was it full of?
Seawater.
Seawater. Okay, so note, just like kind of make a little note that I made it. The gamma of seawater is about 64 pounds per cubic feet. So that would change your answers ever so slightly all the way through. I have to change that on my key. Oh, never mind. I did it correctly on my key. So if where I put the gamma in, you just change that to a 64. The rest of the numbers are correct. I just wrote down 62.4. All right. So in this case, we're dealing with this thing and it's full of water. And what I want to know is required. I just want to know, well, let me put the required down here. I just want to know the force of pressure on the end. Or I guess we'll just put F of P equals what? Okay. So what we need to do in this case is, so again, like this is pretty complicated, right? Like if I were to try to just do this with like an integral, like you can imagine like there's a bunch of like little tiny triangle arrows pushing on this face right here. And as you get down towards the bottom, they're going to be, they're going to get larger, right? So it'd be really hard for me to draw the pressure prism right here. I don't even know why I'm trying, right? But I am trying a little bit. Right? You can see that as you get deeper, the pressure is going to get stronger and stronger. It's really hard to draw that pressure prism, right? But luckily we have these equations and they work for us. So here's our tools, right? So we just need to remember what are our tools. Okay, so let's do this. Solution. Okay, what are my tools here? Well, I don't even need a free body diagram here because it's not asking me to like solve for anything. I'm not going to need to sum forces, but we just need to know that FP equals gamma HCA. Okay. Now it didn't ask where it was acting, but I'm going to go ahead and add that to this problem. We'll go ahead and solve for that as well. Okay, so YCP, where it's acting, equals, let's see, so that's YC plus IXX over YCA. Okay, so we're going to go ahead and solve both of these. So what I want to do is the way I always do this, and this is an aside. Okay, I do it as an aside, like sometimes like I'll fold my paper in half and I just work the aside somewhere off to the side. And I'm just going to think about this shape. Okay, the shape that I'm looking at, and it is a semicircle. So it looks like this. Okay, so that means I'm going to have to go to a chart somewhere. And I'm going to figure out I'm going to have to figure these things out. And so what I'm going to note is that if I go and I look at a, one of these charts, okay, the centroid is probably here, and it's probably closer to the flat side than the not flat side. And so what we're going to do is, well, we need to know how much. Okay, so let's see. So we're going to do H sub C. Okay, in this case, the H sub C and the Y sub C are the same because the face is vertical. Okay, so we're measuring along the same thing. So H sub C and Y sub C are going to be the same. They're going to go from here to there. Okay. Now, that's not a simple question, though. So what we actually have to do is we actually have to go to a chart. And there's an equation for where the centroid is in a semicircle. And it's 4/3 R over pi. That's super annoying. Okay, but it's not like difficult. We just, we've got a calculator. So instead of R, I'm going to plug in 5 meters because I have that from over here. It's given. Okay, so well, I'm just going to plug that in my calculator. So let's see. So that's 20 over 3 pi. 20 divided by, in parentheses, 3 times, where's pi on here? Pi. Okay, I'm gonna 2.1221. 2.1221. Okay, and that's meters. Okay, and this is going to be the same number. Okay, note that again, they're the same because it's vertical. Okay, the IXX, I guess usually I do area first, don't I? Do area. So area is the area of a circle divided by 2. Again, I'm going to plug the 5 in. I'm not going to like write that out for you. So what's that? 12.5 times pi. 12.5 pi is 39.270 meters squared. And then what else do I need? Oh, I need this this moment of inertia, right? So we'll go IXX. Okay, and that's going to be, so again, we get this off the chart, 0.110 r to the 4th. Again, I'm not going to show y'all me doing that work. I'm just going to go 5 times 5 is 25, times 5 is 625, times 5 is, I don't really remember. What's 5 times 625? It should be easy. 3125 times 0.110. And we get, whoa, I get a different number than I got in my notes. That's interesting. What's 5 to the 4th? 625, okay. Is that right? Oh yeah, it is, okay. Times 0.110, okay. 68, oh no. 68.75, okay, meters to the 4th. All right, so now we're just gonna solve those forces. And once we do that, this is plug and chug. We're just gonna plug into these equations. Okay, and that's why I kind of like to isolate the shape. Because at this point on a test, right, now you're just rolling, right? FP equals gamma HCA. Like this is like the mindless part. FP equals gamma. Well, it's water, 62.4 PCF. HC right here, 2.1221 meters. Okay, area. Well, I didn't leave myself a lot of space here. 39.270 meters squared. Okay, pounds per cubic feet times cubic. Oh no. Okay, this is why we put our units on these things. Because sometimes we use the wrong one. Okay, I use PCF. We are in the metric system. Okay, so this is going to be 9810 newtons per meter cubed. Okay, meters cubed are going to cancel with meters cubed and be left with meters or newtons, excuse me. And so this is, well, I'm just going to give it to you in 3 sig figs, 816 kilonewtons. Okay. And if I wanted to know where it acts, and this is measured from the surface, okay, so this is measured downwards to the YCP, okay, and I would go YCP equals the Y bar, or the YC, 2.1221 meters plus I bar, or IXX, that's this one, 68.75 meters to the 4th. Divided by, let's see, YC, 2.1221 meters times the area, which is this number right here, 39.270 meters squared. Okay, sorry, it's a little squeaked in there. But the YCP equals, so in this case, you wouldn't really care about how much deeper it is than the Y centroid, because you're not asked to do any like, you're not asked to do any moments or anything. 0.1221 plus 68.75 divided by 2.1. And to 3 sig figs, it's 2.95 meters. Okay. And again, we don't even have to keep the 5 here because we're not, we're not doing anything with these calculations. But if you were to do something with these numbers for calculations, like a moment or something, I would want you to keep 5. Okay. The way I look at it is, if I grade you to 2, but you round to 3, but you keep 5, you won't ever make a mistake. You'll be golden. So any questions?
There's going to be, when it comes, I was just thinking about logistics in terms of practicing and all of that. We have homework problems and we have concept questions, and then we have the problems we've worked in class. And I'm assuming that, for example, if we have a lesson, if we have a different kind of section every class, are we looking at doing problems, like, for example, let's say one problem covers 2 sections, because you can apply everything that we've done in those 2 sections to a problem. I'm just curious to see, like, for example, you wanted to use a different shape. This is a semicircle. Is that something in terms of like, that's how you're going to see that variety on the test problems that you were discussing?
For these, I can vary these problems in a number of different ways. So I can give it, so like, I just showed you most of the variation. So I can change the fluid. I can change the shape from rectangular to triangular to like whatever. I can change the angle. Okay, this one was vertical. The last one was on an angle. What else can I alter? Let's look at these equations. Yeah, that's most of it. And then usually I do moments around these things. That's the way most of these things are acting. So it's kind of, where's the hinge? Where is the hinge? And that's kind of really like, if the hinge is on the top or the bottom. And what I did on the last one is I just tried to put the hinge in some place that would be interesting, right? If I give you an interesting spot, or like I would try to put the hinge in a place that makes you think a little bit. Like if I were to turn this one into a hinge problem, if I put the hinge right here, okay, then the force is acting right here, coming out, right? And its moment arm then is YCP. Whereas I would prefer to somehow put the hinge on the bottom, which in this case I wouldn't be able to do. So that would force you to show me you understand what that YCP means by subtracting out, like, 5 minus 2.95 would be this distance right here. So that would be 2.05 meters. But obviously in this case, I can't really put a hinge on the bottom. That's kind of unrealistic, right? So maybe what I could do is have the gate look like this in the bottom of a fluid like this and put the hinge here, right? And then your YCP is to this point right here. That's a more difficult problem. So but that's what I would vary in my questions, just to make sure that like you've caught on to what you need to catch on.
Right, that's what I was asking. Last question I have. I was thinking about way earlier in the lesson today about this concept that as you go further down, like depending on the shape, you have triangles, rectangles, that kind of thing. And I wanted to know, in my head, I was thinking to myself, if you go down to the base of a triangle, you're going to have the most force. But let's say in a rectangle, is the force more uniform, although it is still going to be the most at the bottom? I was asking more about how shapes affect the uniformity of the force within the object entirely, or the fluid entirely within the object.
Okay, I think I get what you're saying. So like right here, if we compare the rectangle to the triangle, and let's suppose the triangle has the same base as the rectangle. Okay, so more or less the same base, right? I think you can see that this area has the most pressure on so the effect of this red line over here and this red line over here is the same. The effect of this red line, so the top portion of it, versus this bit over here is not the same.
Okay, all right, I see.
So on the triangle, what's going to happen is the centroid or the center of pressure here is going to be it's going to be more influenced by its bottom bit than this one. So the centroid of the triangle, if you remember from your centroids, why I wanted to erase that black dot, I don't know. Anyway, the centroid of this one is like right, come on, man. Okay, so the centroid here is like right here. The centroid of the triangle is closer to the bottom. I believe it's 1/3 of the way up, right? And the center of pressure of this one, let's do that in, let's say, green, is usually, oh man. Okay, the center of pressure of this one is like, it's usually, this is a vertical face. Well, I don't want to say what it usually is because I'll confuse some of you, but it's just a little bit behind it. This one is much more affected by its bottom than by its top. Okay, so it's probably going to be potentially a little bit further down. I haven't done that math, but you're right. This shape right here is much more affected by its bottom end than its top end. And by its centroid is further down. And I think, that of course is going to have an effect on where the center of pressure is. So,
Thank you so much. I was just curious in terms of conceptual thinking and how that's applied. And I appreciate you showing me that diagram. It helps me understand exactly what I was asking. So thank you.
yeah, you're welcome. And it also kind of looks like a little Christmas hat.
It's cute.
Yeah. Any other questions? So I will send you guys a link probably today of videos that you should watch on Saturday. If these make perfect sense to you, then no worries. If not, I'm going to try to find somebody who's going to work out one with a planar face and I'll try to find somebody who works one with a curve. The curved face is much more difficult. So note in this case, this face looks like it's curved, but the face itself is flat. Like this face is flat. It's just got curved edges. Okay. When we do curved surfaces, what that's going to mean is, like, let's imagine you have a levee that is shaped like this. Let's say the water is kind of lapping up against it. Say this is a levee. Trying to draw this as best I can. So this is the water over here, and it's pushing up against that levee. And so you can see that the shape of the levee itself is kind of like, like this is the I don't know, it's a weird shape, right? So we'll talk about that next class. It's actually one of my favorite things because it's very clever, whoever figured out how to solve it, in my opinion. So anyway, that's all you got. I have to sit in a university training for the next hour. I'm looking forward to it. It's going to be very exciting.
Good luck.
Oh, I have a question about Saturday.
Okay, yeah.
We're meeting on Zoom and same time as usual?
No, we won't meet on Zoom. It has to be, I'm pretty sure that the thing said not to make it asynchronous. So it's going to be completely asynchronous. Watch it on your own. If you want to come to like an office hours or something like that afterwards, and I'll do the whole thing with you. But basically what I'm going to do is I'm just going to give you 2 other videos of people who are not me presenting this same information. I think it can be helpful to kind of just see somebody else, because sometimes somebody will just say something and be like, aha, that one little thing was, speaks the way that I think, so.
Right. Okay, great. Thank you.
Okay. And again, if you guys want me to do it, come on in, I'll do it. Yeah, so. All right, well, if there's no other questions, I'll see you guys Thursday.
See you Thursday.
Thank
All right,
you.
see you guys.
Thank you.
Thanks, guys. The recording.